Let's look at tree traversal. That is, given a binary tree, we would like to visit all nodes in the tree, but in a specific order. That order could be pre-order traversal, post-order traversal, or in-order traversal. Let's first start with the pre-order traversal. Pre-order traversal means while visiting any node, we first would like to process that node. That means whatever visiting that node means, do that. For the example here, processing a node for us will mean printing the value of that node, but it could be anything. Just process that node. And after you're done processing that node, visit its left node and repeat the whole process there in a recursive manner. And when you're done with the left child, this time repeat it with the right child, again in a recursive manner. So let's see the example. As we said in this example, visiting a node for us means printing the value inside the node. So we start with the tree given here for us. So we have C at the root. So our current node is C. Visiting that node means writing on the screen C. Then we should visit its left node. Its left node is O. So we're not here anymore, but we're at O. So first process this, so write it on the screen, and visit its left node, which means not here, but here now. So write M, then come to P, write P. Now we're done with P. So when you want to visit its left node is null. So we cannot go to the left node. The algorithm says if when you're done with the left, look at the right node. So look at the right node of P, but that's also null. So that means we're done with P. We have processed P. We've tried to process its left child, but that was null. We've tried to process its right child. That was also null. So we're done with P. Therefore, we're done with the left child of M. So we return back to M. And now look at its right child, which is U. So we're currently in U. So process U. Try its left child, but the left child is null. Try its right child is null. So we're done. We return back to M, and we have processed M, processed its left child P, processed its right child U. So we're done with M. Therefore, we roll back to O. Its right child is null. Therefore, we're also done with O. This way, we're done with the left child of C. So we look at the right child of C, which is T. So we write T, try its left child, but that's null. So try its right child, which is E. So write E, try its left child, R. Right child is L. Left child of L is A. Its left child is null. Right child is null. So you roll back and now try N. Left child is D. Its left child is null. Right child of D is also null. So we are done with the left child of N. Roll back to N and try its right child, which is null. So we are done with N. Therefore, we roll back to L. We are done with L. We are done with E. We are done with T. We are done with C, which means we are done with the whole tree. And the output of the tree would be computer land if it is visited in the pre-order traversal. So I hope this explains all. So let's start with U, but pay attention, we're not processing it yet. First, visit its left child, which is P. Visit its left child, O. Visit its left child, C. Visit its left child, which is null. So we're done with the left child. Roll back. When you roll back before visiting the right child, you first process C, so you write C. Visit right child, which is null. We're done with C. Roll back. Now we're done with the left child of O. Before visiting its right child, we should first process O. Then we visit its right child, which is M. Its left child is null, so process M. Then visit its right child, which is null. Roll back to O. Roll back to P. So first process P, then visit its right child, which is null. Roll back to P, roll back to U. Now process U, and then visit its right child, which is T, but before processing T, visit its left child, which is null. Now process T, visit right child R, visit left child E, visit left child null, process E, right child is null, roll back to E, roll back to R, and process R. Now visit right child A, but before processing visit its left child L, visit left null, process L, right child is null, roll back to A, process A, go to right child D, go to left child N, left child null, process N, visit right child null, roll back to N, roll back to D, process D, roll back to right child, visit right child, which is null. So we're done with D, roll back to A, roll back to R, roll back to T, roll back to U. And again, the output is the same, but pay attention, the output, the input tree in this one, and the input tree, let me get the, I'm sorry, I should get the pen. Okay, here we go. So you have a stack, and in the stack, what you have is actually these. At the bottom, you have multiplication, 3, addition, 2, and on top of that, you have 1. Now, the first thing we do is we pop one value out. So let's say I had two variables, A and B. So we pop one out and write it in B. Then we pop the next value from the stack and write it in B. We do now pop the next element, which is addition. Okay, I should be adding 1 and 2. The result is 3. So I push the value back on the stack as we did. Sorry. I picked the wrong item. As we did in the previous chapter, remember we were adding the two values and pushing the result back into the stack. We apply the same idea. So put the result in here. Now, again, repeat it. Pop one element, which was 3, and write it here in A. Pop the next element, which is also 3, put it in B. Now pop the next element, which is multiplication. So you should do multiplication, and the result is 9, and you put the result in the stack. And we are done. So converting from the infix notation to the postfix notation helps us, and we put this postfix notation. Once again, let me draw the stack. Remember, before doing the execution, the stack was just actually this postfix expression. Now the processing is very easy. Pop element, pop element, pop operator, do the operation, push the result, and repeat it. This works for all kinds of expressions. So in our program, we don't need to deal with what kind of an expression we have in our program. So, sorry, let me. Here we have a project for the implementation of the translation from infix notation to postfix notation. I will not go over this in the project, but this is an important example. Please download this project and analyze it, go over it carefully. It's important that you understand it. Let's look at how we do the depth-first search traversal and the breadth-first search traversal, since these are two important ways of visiting the nodes or searching for a node in a tree. So depth-first search is actually what we have already done. So we start from the root and try to visit the nodes one by one. First, trying to go as deep as possible through the left child. So you start from the root, you go left, 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 all the way down until you hit a leaf. When you come to a leaf, since it doesn't have any children, you cannot go further. So you roll one step back and visit the right child and repeat it there. When you're done with the right child, take one more step back and again repeat it recursively for the right child. So this is actually what we have done, as I said, up to now. Breadth-first search is different than depth-first search. In the case of breadth-first search, rather than trying to go as deep as possible, instead we're looking at we're visiting the elements level by level. Well, in level 0, it's obvious there's only the root in level 0, so it's trivial. Level 1 is also trivial because they're the left and right children of the root. But when you come to level 2, things start getting ugly. Now, let's open the project, and in the project, it will be easier to explain it. Let me just open it. Now, we're in 3 main Java. In 3 main Java, look at the main method first. In the main method, we're creating a tree. It's of type myTree, which is already in here. Okay, it's simple. It just has an add method. It's just placing the elements in what we call the binary search tree order, as we will see soon. So it's just creating a tree by adding these nodes into the tree, and then it's displaying it in graphics. I will not go into how you draw a tree in graphics. It's already in here, binary tree view. If you want, you can just deal with that, but we'll skip that. But anyways, this will just create a tree and display it in graphics, as we'll see now. And then on that tree, when the tree is visible for us, we will look at how we do depth first search first, then breadth first search traversal. In each case, the depth first search traversal will place the nodes in the tree into a linked list, into an array list with the name DFS order. DFS order, as you can see, it is defined here as an array list of integers. Okay, so depth first search places the elements into this array list, and breadth first search will place them into the other array list, which is the BFS order. Okay, so let's first run the program. Let me run 3 main Java as a Java application. I have two monitors, so the graphic has went to the other monitors. This is it. So this is a tree. So we are entering these values, and this tree is created. Change the values here, and a new tree will be created here. Okay? When you're done, don't forget to click this to close this graphical display. Anyways, we're given this tree. Now we want to traverse it in the depth first search order. Well, if you traverse it in the depth first search order, the result is also displayed here because we have this print line here. So the first line is for the depth first search traversal of the tree, and the second line is the breadth first search traversal. Depth first search is easy. Visit 15, visit 6, 3, you're done. Roll back 9, 8, roll back 13, roll back, roll back, roll back 24, 18, roll back 28, 26, roll back 29. Then roll back, roll back, roll back, and we're done. Okay. Now, how is it implemented? It's quite easy. We start with an empty DFS order array list. So you first add the current parameter, which comes as root, the value field of it, into the array list. So it will be 15 for us. Then recursively call the same method, this time changing the root to the left child of the root, which is 6. So repeat it for 6. That means don't see the other side of the tree, just look at this side and repeat the same process. So it will put 6 in the array list. Then repeat it for 3, so it will put 3 in the array list. So we have placed 15, 6, and 3. When we're done, the 3 does not have left and right children, so it will fall into this if statement here and immediately return. We're done, so it will call it for the right child of 6, which is 9. Then that will call it for its left child, which is 8. That will be done. Roll back, call it for 13 of 9, the right child of 9, which is 13. And repeat this process. So it will just display 15, 6, 3. You can follow it here. 9, 8, 13, roll back, 24, 18, 28, 26, and 29. That's simple. How about the breadth first search traversal? Well, that's a little bit more complex, but not too complex either. This time I have to maintain a separate queue. The queue, you could implement it either using the queue class, or what I did simply was using the linked list, because in the case of linked list, if I always remove from the head and add to the end, it would work as a regular FIFO queue. So that's what we're doing here. First, take the current parameter root and put it in the queue. I had an empty queue, so put it in the queue. So at the moment in the queue, I just have 15. So now the loop starts. What does the loop here say? The loop says, take one element out of the queue. I had 15 in it, so remove it at the moment queue is empty. And process it. For the processing, we add it into the BFS order array list. So put it in the list, and then if the left child is not null, if there's a left child, put it in the queue. Pay attention. The list is the real order. Queue is something I use temporarily inside the method. So put its left child in the queue. That is, when I'm looking at the queue, I should continue in that order. Remember, I had removed 15 from the queue, so 6 is the only element in the queue at the moment. Then repeat it for the right child, which is 24. So at the moment in the queue, I have only 6 and 24. And I've reached the end of the while loop. Come back. Is the queue empty? No, there's 6 and 24. So take the first one out, 6. Now, put 6 in BFS order, but before continuing with 24, put 3 and 9 in the queue. What's in the queue before you put 3? 24 was in the queue, so 3 goes behind 24 and 9 goes behind 3. So in the queue at the moment I have 24 and 3 and then 9. Now pop one out, which is 24. Process that. So put 24 in the array list and put its elements in the queue after 9 actually. So at the moment in the queue I have 3, 9, 18 and 28. So it works this way until the queue becomes empty and the output is as given in here. Okay, so that completes the example, and this is also the end of this section.